Today we will consider as application of Maxwell's thermodynamic relations this problem. Establish following relation. To establish this relation, Cp minus Cv equal to T delta P upon delta T at constant V into delta V upon delta T at constant P. And using this, we will prove that Cp minus Cv equal to T Et alpha square V. And we will find the value of Cp minus Cv for ideal gas and for real gas. For ideal gas, Cp minus Cv equal to R, and for real gas, Cp minus Cv equal to R into 1 minus 2A upon RTV. First of all, we will prove this relation Cp minus Cv equal to T delta P upon delta T at constant V into delta V upon delta T at constant P. Cp and Cv, these are molar specific heats. Cp is for constant pressure P and Cv is for constant volume V. And definition of molar specific heat is this. We write molar specific heat by capital C, and it is equal to delta Q upon delta T. It is from the definition of specific heat, which comes from the relation dq equal to mc dt, where we write C as small c, and that is specific heat. If we write mass in moles, and for 1 mole gas we find specific heat, that is molar specific heat. We write molar specific heat by capital C, and for 1 mole mass it is delta Q upon delta T. There are two types of molar specific heats. One is Cp and other is Cv. Cp is for constant P, so Cp is equal to delta Q upon delta T at constant P. This is equation 1. And Cv is equal to delta Q upon delta T at constant V. This is equation 2. Now from second law of thermodynamics, we have dq equal to T ds. So put the value of delta Q equal to T delta S. These two equations for Cp and Cv now becomes Cp equal to delta Q upon delta T at constant P. It is equal to T delta S upon delta T at constant P. Here we write delta Q equal to T delta S from second law of thermodynamics, dq equal to T ds, or from the definition of entropy, change in entropy ds equal to dq upon T. Similarly, we have for Cv, it is delta Q upon delta T at constant V, and it is equal to T delta S upon delta T at constant V. We write these equations for Cp and Cv as equation 3 and equation 4. Now Cp minus Cv now becomes T delta S upon delta T at constant P minus T delta S upon delta T at constant V. But we have to prove that Cp minus Cv is T delta P upon delta T at constant V into delta V upon delta T at constant P. In this expression, entropy S is not here. So we have to eliminate entropy S from this expression. To eliminate S from this expression, we write entropy S as a function of T and V. There are 4 thermodynamic variables P, V, T and S. We can write any of these 4 thermodynamic variables as function of other 2 thermodynamic variables. So we write here S as a function of T and V. This is the expression for Cp minus Cv. In right hand side, in last term, we have delta S upon delta T at constant V. So remember, from here we write S as a function of T and V. Remember the order, S T V, delta S upon delta T at constant V, S T V. So we write S as a function of T and V. Now if we differentiate this, then ds will be equal to delta S upon delta T dt plus delta S upon delta V dV. Since S is a function of T and V, so we differentiate once with T and then with V and get ds equal to delta S upon delta T into dt plus delta S upon delta V into dV. In the first term, where partial differentiation is with respect to T, we keep V constant, and in the second term, where partial differentiation is with respect to V, we keep T constant. Now partial differentiation of above equation with temperature T at constant pressure P gives this is ds, and now we find the partial differentiation with respect to T and keeping P constant. This we can do by dividing this equation by dt. If we divide this equation by dt, in left hand side we get ds upon dt and we write it as delta S upon delta T. If we divide this by dt, then left hand side is ds upon dt, which we write as delta S upon delta T. In right hand side, when we divided by dt, the first term will remains delta S upon delta T at constant V, and if we divide by dt, second term will become delta S upon delta V at constant t into dV upon dt, and we write this dV upon dt as delta V upon delta t, and this we do for constant V, for constant pressure P. So we write delta S upon delta T at constant P equal to delta S upon delta T at constant V plus delta S upon delta V at constant T into delta V upon delta T at constant P. Put constant P in left hand side term and in the second term of right hand side. So partial differentiation of this equation with respect to t at constant p gives this relation. Now we have delta S upon delta t at constant p minus delta S upon delta t at constant v equal to delta S upon delta v at constant t into delta v upon delta t at constant p. If we multiply by t, the left hand side will become Cp minus Cv. So we multiply by t in left hand side and right hand side. Left hand side now becomes Cp minus Cv using equations 3 and 4, and now Cp minus Cv is equal to T delta S upon delta V at constant T into delta V upon delta T at constant P. But we have to eliminate S in right hand side, and S appears in first partial differentiation delta S upon delta V at constant t. This S can be eliminated by using Maxwell's thermodynamic relation. From Maxwell's second thermodynamic relation, we have delta P upon delta T at constant V equal to delta S upon delta V at constant T. So from this thermodynamic relation, we put the value of delta S upon delta V at constant T, which is equal to delta P upon delta T at constant V. If we put the value of delta S upon delta V at constant T from Maxwell's thermodynamic relation, we get Cp minus Cv equal to T delta P upon delta T at constant V into delta V upon delta T at constant P. So this is what we want to prove. Cp minus Cv equal to T delta P upon delta T at constant V into delta V upon delta T at constant P. Now using this relation, we want to prove that Cp minus Cv equal to T Et alpha square V. Here we have two terms Et and alpha. E is bulk modulus. Bulk modulus E, this is the definition of bulk modulus. It is ratio of normal stress and volume strain. Modulus of elasticity is equal to stress upon strain, and when we have volume strain, this modulus of elasticity will be called as bulk modulus. So bulk modulus E equal to normal stress upon volume strain. Stress is delta P, change in pressure. Pressure is force per unit area and stress is also force per unit area. So we write stress as delta P, change in pressure. And when pressure is changed, volume is also changed. And we have a volume strain, and volume strain is delta V upon V. Volume strain is change in volume upon original volume. Change in volume is delta V, original volume is V. So for normal stress we write delta P, and for volume strain we write delta V upon V. And a negative sign is introduced because when P increases, V will be decreases. When we increase the pressure on a body, its volume will be decreases. So we write a minus sign so that the bulk modulus capital E will become positive. Now this bulk modulus E is equal to minus V delta P upon delta V. This is E, but we use here ET. ET is bulk modulus for constant temperature. For constant temperature, we write ET as minus V delta P upon delta V at constant T. We write constant T. So this is the bulk modulus for a process where temperature T remains constant, that is for isothermal process. So it is the bulk modulus for isothermal process in which temperature T remains constant. So this is the term ET, bulk modulus at constant temperature for isothermal process. And the second term is alpha. Alpha in this relation is volume expansion coefficient. If temperature T is increased, then increase in volume of a body delta V will be proportional to V into delta T. Temperature is increased by delta T, then change in volume will be proportional to original volume V and this change in temperature delta T. And delta V equal to, we write it alpha V delta T. Alpha is proportionality constant and it is known as volume expansion coefficient. So from this definition, delta V equal to alpha V delta T, we have alpha equal to 1 upon V delta V upon delta T. And this is for constant pressure P. For constant pressure P, delta V is proportional to V delta T. So alpha, which is constant of proportionality known as volume expansion coefficient, this is the definition of alpha, volume expansion coefficient, 1 upon V delta V upon delta T at constant P. Now we want to prove that Cp minus Cv equal to T alpha square V. We have already proved that Cp minus Cv equal to T delta P upon delta T at constant V into delta V upon delta T at constant P. Now we want to prove Cp minus Cv equal to T alpha square V. We have defined Et, we have defined alpha, put the values of Et and alpha in the right hand side of this relation T alpha square V. Then T alpha square V becomes equal to this. Here we have put the value of Et. After T it is Et. Then we put the value of alpha. Here it is alpha square and into V. V square is cancelled out in numerator and denominator, and T alpha square V is equal to this thing minus T delta P upon delta V at constant T into delta V upon delta T at constant P square. We already proved that Cp minus Cv equal to T delta P upon delta T at constant V into delta V upon delta T at constant P. Here we have two partial differentiations. One is delta P upon delta T, other is delta V upon delta T. And here we have delta P upon delta V and delta V upon delta T. So delta V upon delta T is already there. We have to eliminate this differentiation, that is delta P upon delta V at constant T. To eliminate this delta P upon delta V at constant T, we write P as a function of T and V. We have to eliminate this term delta P upon delta V at constant T. So we write P as a function of V and T or T and V. Its differentiation dP will be delta P upon delta T at constant V into dt plus delta P upon delta V at constant T into dV. P is a function of T and V. So we make differentiation first with respect to T and then with respect to V. So dP is equal to delta P upon delta T into dt plus delta P upon delta V into dV. When differentiation is with respect to T, V is constant, and when differentiation is with respect to V, then T is constant. Now for constant pressure, if pressure P is constant, then this dP is equal to 0. Left hand side is equal to 0, then right hand side will also be 0. And then we have this relation. Keep one term to right hand side, then we get this relation. And from this relation we get delta P upon delta T at constant V is equal to minus delta P upon delta V at constant T into delta V upon delta T at constant P. Here we take dt from left hand side to right hand side, then it will become dV upon dt. We write it as delta V upon delta T. And since this is for constant pressure P, so we write constant P, because for constant pressure P, dP is 0, for which we get this relation. Now we have delta P upon delta T at constant V equal to this thing. Put this value in this relation in equation 7, where we have Cp minus Cv equal to T delta P upon delta T V into delta V upon delta Tp. Put the value of delta P upon delta T at constant V here. This becomes this. It becomes equal to minus T delta P upon delta V at constant T into delta V upon delta T at constant P square. And it is T Et alpha square V, which we have proved here. T Et alpha square V is also equal to this term. So Cp minus Cv is equal to T Et alpha square V. Now we want to find the value of Cp minus Cv for ideal gas, and we will prove that for ideal gas Cp minus Cv equal to R. For this we will use this relation Cp minus Cv equal to T delta P upon delta T at constant V into delta V upon delta T at constant V. and we put the values of delta p upon delta t at constant v and delta v upon delta t at constant p in this relation. For ideal gas, for 1 mole ideal gas, we have PV equal to RT, and using this relation PV equal to RT, we will find the value of P, so that this first differentiation delta P upon delta T at constant V is obtained, and from PV equal to RT we also write the value of V. From that we can find the value of delta V upon delta T at constant P. So from PV equal to RT, equation of state of 1 mole ideal gas, PV equal to RT, we write the value of P and V. P is RT upon V and V is RT upon P, and find these two partial differentiations, delta P upon delta T at constant V and delta V upon delta T at constant P. So P is RT upon V, delta P upon delta T at constant V will becomes equal to R upon V. R is constant, V is also taken constant. So differentiation with respect to T gives R upon V. Similarly, from V equal to RT upon P, we write delta V upon delta T at constant P equal to R upon P. Put these two values and we get Cp minus Cv equal to T R upon V into R upon P. It is T R square upon Vp, and Vp is equal to RT, Pv equal to RT. So in denominator we write Pv equal to RT. T is cancelled out, one R is also cancelled, and we get Cp minus Cv equal to R for ideal gas. Now for real gas, we want to find Cp minus Cv. Then for real gas, we will use van der Waals equation of state. Van der Waals equation of state for 1 mole gas, real gas, is this. For ideal gas, we have PV equal to RT. For real gas, we have van der Waals equation of state, and here P is now replaced by P plus A upon V square, and V is replaced by V minus P. A and B are constants. Now from this relation we have P plus A upon V square equal to RT upon V minus B. And from this relation we can find delta P upon delta T at constant V. If V is assumed constant, then partial differentiation of P with respect to T will give RT upon V minus B. V is constant, so the partial differentiation of second term in left hand side is 0. And partial differentiation of first term is delta P upon delta T at constant V, and it is equal to RT upon V minus B. This is one of the partial differentiation which we want. Other is delta V upon delta T at constant P. It is the partial differentiation of V with respect to T. To find this, we differentiate partially V with respect to T, keeping P constant. V appears in these two terms in left hand side. First term is P plus A upon V square, it consists V, and second term is V minus B. So we differentiate it using the formula first function differentiation of second plus second function differentiation of first. First function is P plus A upon V square, second function is V minus B. So we have first function P plus A upon V square Differentiation of second will give delta V upon delta T at constant P, plus second function B minus B, and differentiation of first, that is first is P plus A upon V square, and differentiation of this will give minus 2A upon V cube delta V upon delta T at constant P. Second function is V minus B, and differentiation of first will give differentiation of P is 0 because P is constant, and differentiation of A upon V square, 1 upon V square, differentiation of 1 upon V square is minus 2 upon V cube. Differentiation of V to the power minus 2, it is minus 2 V to the power minus 3. It is minus 2 upon V cube. So we have minus 2A upon V cube into delta V upon delta T at constant P. And this is equal to R. Differentiation with respect to T, differentiation of V with respect to T is equal to R. In right hand side we have RT, differentiation with respect to T gives R. In left hand side we have the two terms of delta V upon delta T at constant P. This is taken common, and the remaining terms with it are P plus A upon V square plus V minus B into minus 2A upon V cube. Now we put the value of P plus A upon V square from this van der Waals equation. P plus A upon V square is equal to RT upon V minus B. We put the value here. In place of P plus A upon V square, we write RT upon V minus B. Second term is minus 2A upon V cube into V minus B into delta V upon delta T at constant P equal to R. This gives the value of delta V upon delta T at constant P. Delta V upon delta T at constant P is equal to R upon RT upon V minus B minus 2A upon V cube into V minus B. Now we put the values of delta P upon delta T at constant V and delta V upon delta T at constant P from equations 18 and 19 in equation 7 and get Cp minus Cv equal to T R upon V minus B into R upon RT upon V minus B minus 2A upon V cube into V minus B. This is equal to R upon V minus B upon RT. It is not V minus B upon R. Write it as V minus B upon RT. RT is in numerator. We take it in denominator, and we have in numerator we have only R. It is this R, and this RT in numerator we bring it into denominator, so that in denominator we have V minus B upon RT. So correct it, it is not V minus B upon R, it is V minus B upon RT. And inside the bracket we have RT upon V minus B minus 2A upon V cube into V minus B. Now multiplies this V minus B upon RT. Then the first term will cancel out and it will become 1, and the second term will become minus 2A upon RT V cube into V minus B square. Now since B is much less than V, A and P are constants and these are small quantities. B is small, so it is small in comparison to V. So B is much less than V. So if we neglect in this term V minus B whole square, then V minus B whole square will become V square, and in denominator we have V cube, so V square cancels and 1 V remains in denominator, and we have this equal to R upon 1 minus 2A upon RTV, and it is equal to R into 1 minus 2A upon RTV to the power minus 1. And if we use binomial expansion, then using the formula 1 minus x to the power n equal to 1 minus nx, and other terms are negligible as 2a upon RTV is a small quantity, 2a is also much less than RTV. So neglecting other higher order terms, we write only two terms, 1 minus x to the power n equal to 1 minus nx, and n is minus 1. So we have this equal to R into 1 minus 2a upon RTV. So for real gas, we have Cp minus Cv equal to R into 1 minus 2a upon RTV.